Oh, you're here. Welcome to the lab.
I'm Jason,
And I'm Devin.
and we are from
SMK Taman.
Alright then, so today we will be conducting 4 experiment. Why? Because it's simple, it's easy, and you can do it at home.
I hope you guys enjoy and learn something new today. In this first experiment, we're gonna play with balloons. Balloons. Well, as you can see, balloons are afraid of sharp objects, as sharp objects will pop them. And being balloons, pins are balloons' worst enemies. Oops.
There's a pin. Okay, never mind.
Okay, as you can see just now, one pin and it causes the balloon to pop. But what happens if you press the balloon against multiple pins? Okay. As you can see, we have set up multiple pins for this experiment. I'm going to use this balloon and press it against these pins. As you can see, they don't pop. I wonder. Alright then, even if you use much force against them, they don't pop.
Wow. I wonder.
Why is this happening?
Well, I think it's because the force to pop a balloon is distributed evenly throughout the area.
Yes, that is correct, Mr. Jason.
Wow.
Bingo! Being balloons, they are very sensitive if there's a pressure acting against them on one concentrated point. However, if the area is bigger, then the pressure and the force is equally being distributed throughout the balloon, thus causing it not to pop. Mr. Jason, I have a question.
Yes, how can I help you?
What do we breathe?
Well, we breathe oxygen.
Really?
Yes.
So, does that mean that the air contains 100% oxygen?
Well, Darren, that is incorrect. Oxygen occupies only 21% of our entire atmospheric gas.
I see. Then what about the other 79%?
Well, the other 79% are actually carbon dioxide, which what we breathe out, nitrogen, and inner gas.
Ah, I see. So, how do we prove that air contains about 20% oxygen?
Well, very good. I'm glad that you asked. So, right now we're going to conduct an experiment to prove that oxygen occupies 21% of our air. Well, first of all, you need a container, fill it with water, then you add your candle. Well, why do we use this? Well, I'm going to explain it to you later. Next, you need a transparent glass cup or a glass, as long as it doesn't melt and it's transparent. Next, let's not forget, you can get a wooden splinter, and if you do not have wooden splinter, you can replace it with a spaghetti. Don't ask me why, because it's flammable. As long as it catches on flame, it's usable. And right now, you also need a lighter to provide a flame for your wooden splinter, or in our case, a spaghetti. And remember kids, it's highly flammable, so beware.
Safety first.
Okay, so first, we shall light the wooden splinter or the spaghetti. Alright, now, Aaron, you may take the honor. Take the glass and cover the entire candle, submerge it into the water. Well, as you can see, the candle extinguishes, and you can observe that the water level rises above 1/5 of the cup. Well, 1/5 times 100% is 20%. So we can say that oxygen occupies 1/5 of the atmospheric gas. And why is that? Well, you see, why do we burn the candle? It's basically to undergo a process which we call combustion. Oxygen is needed for combustion, and therefore the oxygen occupied in the glass will be consumed. And once the oxygen is consumed, there have no longer any oxygen left in the cup for the flame to keep going. Therefore, the combustion has been put to a stop, and the gas is used up. And therefore, you can see that the candle extinguishes. And what about the rest of the gas? As you can see, when oxygen used up, if it's 100%, the cup should be filled up with with water. Well, as from our previous observation, there's 1/5 of the gas in the cup has been used. 4/5 of the gas in the cup is a remaining gas, which are carbon dioxide, inner gas, and not forgetting nitrogen. Well, Darren, what do you learn from this experiment?
Well, Mr. Jason, I have learned that air contains 20% oxygen.
Very well then. So, kids, remember, whenever someone tells you that our atmospheric gas is full of oxygen, tell them that it's incorrect. And you can prove them by using our experiment. I hope you guys have learned something today. Thank you.
Yes! Well, we are outside.
Wait, are we playing football?
No, we are not. We are doing science.
Dang. Alright, so what are we doing today?
Well, today we're going to show the water transport in plants, more specifically flowers.
Well, if I have not mistaken, when I was in Form 3, our teacher taught us that water is transferred through the xylem tissue in the plant.
Yes, that is correct. Bingo! And what plants undergo constant transpiration, and this causes plants to lose water almost constantly. And when plants loses water, they have to replace it. Therefore, water is absorbed at the end of the plant, which is normally the roots, or here, this tiny little bud here.
Alright, so how are we going to do this experiment?
Well, I want to show you the water transport in plants by using colored water. Therefore, you will need a plastic container.
Alright.
And then you will need food coloring. Obviously, a flower.
And let's not forget water.
Yes.
Alright then, so let's get started, shall we?
Yes, we should. To do this experiment, first you need to fill up this plastic container with water.
And let's not forget to etch the coloring later. Now, we shall get a pinch of coloring. And stir it.
After the water is completely colored, put the flower into the water.
Okay.
Okay, and now we wait. Enjoy this time lapse of the flower.
So guys, after a few hours of entertaining experiment, our flower turned from this
Into this.
Yeah, it's super cool, but it's not tasty. To the next experiment! So, hi Darren, so what are we doing today?
Well, Mr. Jason, today we are going to do super cooling of water.
Super cooling. Do you mean the latest movie, Batman vs Superman, where Superman is super cool? That's a no. Okay, so explain what's supercooling.
Well, Mr. Jason, I am glad you asked. Supercooling is a process of chilling a liquid below its freezing point without turning into a solid.
Okay, so as I can see, there's distilled water here. So why are we using distilled water?
Well, Mr. Jason, water have a hard time finding the correct position to start crystallize, and this position is known as the nucleation site.
So basically, you mean that we can't use mineral water because they contain impurities that will act as a site of nucleation?
Yes, precisely, Mr. Jason. Well done.
Bingo! Alright then, so how does this supercooling start?
Well, we'll first need a water bottle with distilled water in it, and remember kids, it must be distilled water. Mineral water cannot be used. And of course, we'll need a freezer.
Well, when it comes to freezer, I've been wondering, how long does it take to freeze it?
Well, we'll only take 2.5 hours.
And why can't we do more?
You see, Mr. Jason, if we freeze the water too long, sooner or later, you'll find the position where you will start crystallizing. We will not want that to happen.
Okay, so basically guys, we are going to need distilled water and we're going to freeze it for 2.5 hours.
So, to the freezer!
To the freezer! Darren, are we done yet?
Nope, we are not done yet.
Is it done yet?
Nope.
Guys, look closely to the water. As you can see, there's still bubble to it. Okay, now I'm going to demonstrate you what does it mean by supercooling.
Unfortunately, we have lost the footage while the water was turning to ice. We thought this experiment has failed when Jason hit the bottle and it did not turn into ice, but it turned out that we have to wait a little while longer. By the time we switched on the camera, it was already ice. As I take out the water from the freezer, you can see that the water is still water, it's not ice. This is because the water is super cold, but it has not yet turned into ice. By heating it, I will start a chain reaction and it will start turning into ice. So, that was it guys. Supercooling of water.
Super cool.
Get it? Super cool.
Yeah, super cool. Okay, let's wrap this up. So I hope you love those 4 experiments that we just conducted. And please do some experiment, and I hope you love the experiment. Well, because it's fun, it's cool, it's awesome, it's science!